thing. So make sure people are stir up some commotion in the chat here if we end up losing each other, if the audio goes out. All right, so here we go. This is what we're covering in exam 2. So we start with the equation sheet because that's a really good place to start, because this is the thing that you have during the exam to remember what we've covered. So we have Newton's second law. So the sum of the forces, let's say in the x direction equals mass times acceleration in the x direction. That's true for the y direction and the z direction. But we also can do tangential and normal coordinates. So this is a reminder of that. And here's a reminder that we could also do it in transverse and we'll just call them polar coordinates. All right, so radial and transverse, that's what I was going to say. Radial and transverse coordinates, aka polar coordinates, we could do that in any of these 3 coordinate systems. That's good to know. This is just a general thing. It says, well, this is the linear momentum of a particle. We haven't covered the angular momentum of a particle, but that's sort of like, they kind of go together, so that's why we put them there. Then they work in energy. I think I replaced this W. I usually use U, capital U now. I don't know if that's changed on the equation sheet. I should take a peek. This is from, according to this the spring 2019 version of this equation sheet. So I might have changed it. I should try to get it there. But here's our kinetic energy, and here's our potential energy thus far as gravity and a spring. All right, so there's 2 different types of potential energy. We also know that there's some work in power, and power can be defined by the force times the velocity. We know that it's the time rate change of work. That's good to know. And later on, it might come up, well, not this time in this exam, but it's also moment times angular velocity. So that's actually like torque times RPM is essentially what that is saying. So efficiency is power output over power input, what you want over what you pay for. And then we have the principles of impulse and momentum, where we have the momentum before plus the impulse that happens to it equals the momentum afterwards. And in some cases, the application of that will become the conservation of momentum. Right, so this will be all the particles, the momentum before equals all the particles momentum afterwards. And then if there's an impact, and we know the coefficient of restitution right here, E, right here, we will see this will be an equation that we will often get. And I kind of don't like using these apostrophe kind of symbols. I kind of don't like, I'd rather have 1 and 2. Or 1, 2, and 3, or whatever, depending on the thing. But this is another way of writing it for the coefficient of restitution. So what have we covered? Particles, Newton's second law, where we had homework 6, class 6 and homework 6, where F equals ma in rectangular coordinates. In class 7, homework 7 was F equals ma path and polar coordinates. Particle, work, energy. We did all of the main work and energy thing with the potential energy, kinetic energy, work added, friction loss, and then we did a little bit more of that with more complication stuff, but maybe had more conservation of energy stuff, power, and efficiency in class 9, homework 9. Impulse, momentum. We know that force times time is impulse, mass times velocity is momentum. And then in class 11, we added collisions and the coefficient of restitution. So, oh no, these were homeworks from last spring, right? So, yeah. Kind of see we didn't do that much many different things. This was the friction stuff and rectangular coordinates. And, yeah, this is a polar coordinates thing, and here's a path coordinates problem. Yeah. And then this is the work and energy stuff, and because there's a spring, that's usually a dead giveaway. That's a good problem for a work and energy. And there's more work and energy, and then this was a power and efficiency problem. Here was an impulse and momentum problem. Here was like a a preliminary collision problem where now the trucks stuck to each other, so you didn't need the coefficient of restitution. And here was a problem where we had impact, just a simple impact. And here's one like we did also with two balls hitting each other from homework 11. And then here's one with like more complicated stuff going on. So there's like a kinds of overview of the types of problems that we're going to cover. Is there any specific questions? Anybody have any specific questions that they would like to see? I'm going to move this guy over here to the side so I can see.
Sure.
If you guys
For the exam prep, question 7. That's one I struggled with it a little bit.
Okay. Is it? Come on. Why aren't you moving?
This one, yeah.
That one. Okay, so we have a work and energy problem. Great. Let me write out the problem. I'll move it over to my other screen so I can see what it looks like here. Where'd you go? There you go. All right. So we have little block here. So this is what is this? Was this problem? I said it's an S17 work energy. Did you say this was problem number 7? I think you did. All right, let's see. So this thing is 6 inches. And it's 16, I guess, between these springs. And the thing we want is this is a 10-pound collar, so the weight of C, I guess that's C, is 10 pounds. And it swings between A and B. If the spring is pushed to the right until spring B compresses 2 inches and released from rest, determine the distance through which the collar will travel if the coefficient of friction between the collar and the rod is 0.42. Interesting. Okay, so in any kind of problem like that, I think it's a really good idea to make like a little sketch maybe. So here's what they're describing. So what this has done is it's compressed the thing by 2 inches. All right, so that's going to be like maybe del 1 that we're going right here. And we're going to, and one thing we should probably, we're going to know, we need to know friction. So we need to know the normal force that's acting onto this. And I'm assuming that this is, yeah, they say slides on a horizontal rod, right? So the rod is horizontal. We don't quite know, but I guess it doesn't matter which direction gravity is. I mean, we could be looking down at this thing, or we could look from the side, but either way, if you do an FBD, of course, this is an unnecessary FBD, but I think you should still do it. The FBD IBD of this thing. You know, we could say like it doesn't matter what the forces are that are being placed onto the thing in the X direction. All we're looking to do is get the weight of C, and then we could say within the collar there is a normal force of C. And then there's no acceleration in the Y direction, so we could just say the sum of the forces in the Y, sum of the forces in the Y direction is equal to 0. So negative WC plus FNC equals 0. And we complete the completely obvious answer that the normal force is equal to the weight. And maybe only Dr. Deal is the kind of a maniac who would continue to write things like that out there. But I try to embed in people's minds that they shouldn't skip steps, right? This is such an easy problem. Yes, you could just say that the normal force equals the weight. But other problems in life, you might say, oh, I just skip doing the FBD, and you burn yourself, but that's okay. So we get the friction force at C is going to be mu K and the normal force. And they didn't tell us anything about the static friction, so that's kind of good because we didn't want to have to deal with that. And trying to find out if whether the thing would move or not, but I think it's a pretty good chance. It's a dynamics problem, so it's not just going to be statically stuck, but that's like something that maybe could happen. All right, so and I kind of drew this kind of messed up. I kind of wish I had I made it look like I lined it up a little bit better. It should look, the wall should look closer because the spring has squished. So we write out our first thing, our KE1 plus our PE1 plus any work that's done between the two positions, and KE2 plus PE2. All right. Something they did give us a hint, and they said the 6 inches of the collar is part of the 16-inch distance between the undeformed springs. So here is something that we have to be prepared for. We have to be prepared for that this collar will actually hit this spring. So we have to kind of like go, okay, what if, and we'll just say, what if it doesn't, right? So it's going to move from, let's say, this position over here to this new position right here, right? So this is the distance, the initial distance we're gonna check for, and because we already can see what the answer is, we know that that's going to be true. But before then, we didn't know if it's actually going to hit the spring or not. But that would be a really long exam problem.
Sir,
Yes, sir.
when they say like B is compressed 2 inches, is it like it will compress B, so B it become 2 inches, or it will be next C, it will be next to B, like difference between them 2 inches?
Let's see. I think I tried to show it in this diagram, right? That it's touching B and now it has moved over. Like here's where B used to be. Like right, well, no, right here's where B is used to be, like right there where you see.
Okay.
Here's where that was, and now we've just picked this up and we've compressed this 2 inches.
So the initial difference between like C and B was 10 inches, so it moved over all 12 inches C.
I guess what you'd say, okay, well, actually, because there's actually only 5 inches in
Oh,
between
five,
here
five,
and
yeah,
here.
yeah, 5 here. I said, so it moved
So
7 inches.
so it has moved 7 inches. Yes.
Okay, yeah, now I understand.
So we take KE1. We're going to be released from rest at 0. The potential energy 1. It doesn't change in the vertical direction, its position. So it's only going to be the spring potential energy right here. This is going to be like state 1, and this is going to be state 2, where it moves from one state to another state. So we can actually, okay, they told us the spring somewhere. They should have. There it is. Okay. Oh, I see. Spring. This guy, they're being a little clever because this was part of probably a problem that had a lot more other stuff going on in it. But this is like spring B is this, and spring A is 18 pounds per inch right there. And so this is going to be the 12 pounds per inch. And yeah, well, okay, I'll go ahead and do this, but we need to recognize when we're done with it, right, that we're going to go 4 times, well, I guess it's going to be like 24, right, inch pounds. But we really should turn it into foot pounds because when we're dealing with work and energy, when it comes to the kinetic energy, we want things because we're going to use mass, right? And so we're going to have to convert something into slugs at some point. And the only way that works out is if we're in a system of units that uses feet, not inches. So it's a minor point, but we're going to divide by 12 inches per foot and get up with 2 foot-pounds of 2 foot-pounds of potential energy. Now, the problem asks us what the distance it will travel before it stops, right? So let's see. First off, we're going to say, I meant to do this one now. Between states 1 and 2, that's going to be friction energy that's going to be lost. That's what's going to make the thing stop.
Sir,
So
in
that's going to
that case,
be,
why did we change it to foot pound? Why didn't we let it like inch pound?
okay, well, we're going to, the truth is we probably could in this case, but we're not gonna, right? It's just a bad thing to do, because if we do have to deal with kinetic energy, we use mass. You know, when we go to mass kinetic energy 1/2 mv squared, then we have to use slugs right here times feet over second squared, right? And when doing that, slugs are particular to feet, and we can't intermix them. And when we get done with this, we will be in foot pounds. Now, the truth is,
Okay.
in this problem, it won't matter. We'll see in a minute, but we didn't know that necessarily starting out. So I'm just cautioning you, do not use inch pounds regularly. Now, maybe in the solution that they show, like I didn't write the solution. I think it was, I just kept the solution that I got at the Coast Guard Academy. But whoever did that, they might have taken a shortcut and recognized that you didn't have to do this in this particular problem. But I'm trying to be cautionary and tell you, watch out. This is where you can get burned in units, because everything we're doing, when it comes to kinematics, or excuse me, kinetics, we always, in the US system, we always use feet because we're using the slug system. And I don't want to make it any more confusing. So I hate to make it confusing by telling you to do this when you're about to see in a minute that it actually isn't necessary in this case. But in many others it will be. So just do what I say, maybe. So okay, so for the work lost here is going to be the friction force times that distance I wrote as d, and it's going to be negative. So we know that's going to be what, negative 4.2 times the distance. And then continuing on, the kinetic energy at state 2, assuming it stops before it hits the spring, but either way, it's going to stop, right? And the potential energy at 2, assuming it doesn't hit the spring, is going to be 0. So what we're going to find here is that we have 0 plus 2 foot-pounds minus FF times, no, not friction, no, we already had that right there, right? 4.2, and D is equal
Sir,
to,
is not the
yes.
D like the 2 or 7, the overall?
That's a good, let's see, what are they asking for? It determined the distance through which the collar will travel. So they didn't say where it was starting from. They just
Ah,
asked the
okay.
distance it's going to travel. So it's probably starting from here.
So okay, so that's the start point for us.
Yes.
Yeah, okay.
It's just the way that the wording of it kind of like makes it, you have to kind of like read between the lines and say, yeah, you know, it's almost got to be like a little lawyer going on here. But anyway, we're going to find that the distance is 2 divided by 4.2, right, which is only going to be 0.4619, but these are going to be feet, so we need to turn it back into inches. So we multiply it by 12, and we get 5.714 inches. And I agree that it seemed weird that we made this conversion right here, but I really did that as a cautionary tale, just to try to tell you, well, it works out this time because there was no kinetic energy involved, right? The kinetic energy, let's see, I meant to put this as 0 as well. The kinetic energy was 0 and 0, and therefore we never had to mess around with this. But if we were to ask like for some velocity for the thing, we would want to have turned this into feet.
The wording
Any questions on
is a
that?
little bit weird, sir. Because of that, I didn't understand like fully the question.
Yeah, but because they gave you the question in inches, you'll probably want to give the answer in inches.
Okay.
And also, it's a fraction of a foot, so that usually when there's a fraction of a foot, we say, oh, let's give it in inches instead.
Okay.
It's a crazy American system of units. I can't explain. I can't justify it, but it exists. Where'd you go? Here's the mouse. I need to make more room up here. I have plenty of room. I don't know why all these cables are in each other's way. Out of my way. What happened there? Okay. Any other questions? Somebody got a specific problem that they want to look at?
Also a problem of the S12, S11.
Where about?
It's down S11.
Yeah, I don't have them in that kind of order, so you gotta give me kind of more of a clue.
Go down a little bit. This one.
This guy?
Yeah.
All right. Yeah, you gotta remember these guys are Coast Guard Academy people, so they like to be on these, have their little boats. You're outfitted your Defender class small boat with a 75 millimeter gun. The total weight of the boat, gun, and ammo rounds is 10,000 pounds. While traveling at an initial speed of 30 feet per second, what they wanted to let you know that's approximately 20 knots, but I don't think that's actually true, but that's okay. You fire one 20-pound round at a speed of 2,000 feet per second in the horizontal direction and 30 degrees to the bow as shown below. What is the resulting speed and direction of the boat after firing this round? All right. So this is an exercise in conservation of momentum. And also they got to play little coasty things. So this is the imp mom from S11. Wow, 10 years ago. All right. I didn't want to do too much. So we got this boat traveling this way right here. I guess the total weight beforehand is going to be 10,000 pounds. And the weight of they call it a round, I guess to go, RND, why not, is 20 pounds. And the initial velocity of let's just call him, I guess go call him boat, B-O-A-T. The initial velocity 1 is going to be 30 feet per second. And the velocity of the round, R and D, we'll say 2, I guess, is going to be 2,000 feet per second. So what we want to do here, I guess I can start with there, is we'll have our initial, we will have our impulse, and we'll have our final. And this is a little hard to explain, but maybe not. Okay. So here is our mass total times our V boat 1. traveling in that direction. At this time right here, the impulse, just as this bullet is about to leave, there's a force, a pressure force that's happening right here. In fact, that pressure force has happened throughout the entire length of this thing, of the barrel, that pressure force. But it's equal and opposite. So that is the instant in which we're saying the impulse is taking place. As soon as that bullet is outside of this thing, there are no longer any impulses, right? The impulse ends as soon as the bullet leaves the barrel. So we have this other state now where we have the mass of, let's say I'll write it this way, tot minus the mass of the round, R and D, I decided to call it, times the velocity. We should make sure that it's clear this is now going to be both X and Y, right? We have to be careful in that. The velocity of the boat 2. And now we have the mass of the round times the velocity of the round. 2. I guess I put them up here, right? I put them up there, yeah. So what we want to do is say the sum of the moments, some of the momentums, excuse me, some of the mass times velocity, the linear momentum, sum of those, plus the impulse is equal to the sum of the momentums afterwards. And so we could do this, these are vectors, so we can have an x direction, which in this case is going to be 0, mass times this. And then we're going to have here, we're going to have 0 here because they're equal and opposite. And that's going to equal, now we're getting confused what we're going to do here, but now we're going to have the mass total minus the mass of the round, R and D, times V boat 2 X. All right, and now unfortunately I've kind of messed this diagram up a little bit. I would have liked to have put in that angle, and I kind of would have wished I started over here to the side. So we're going to say plus this momentum, which is going to be the mass of the round times the velocity of the round 2, but only in the horizontal direction. So that's going to be times the sine of 30.
Sir, but
Yeah.
the initial boat has a velocity.
Not in the x direction. Not if I call that
Oh, yeah,
I.
yeah. Okay, okay. It's the
Yeah.
Y. Okay, sorry, I didn't see the X.
No, I hadn't written it yet. Sorry, I should have written it. And that's another thing we should do probably every time with an initial impulse and final in an impulse momentum diagram. We want to make sure that we're explicit as to the coordinate that system that we're working with. So we stick in here equals, and then this is going to be the weight. The total weight is 10,000 pounds minus 20 pounds, but we want mass, so we need to divide by 32.2. We're going to see that that's not going to matter actually, but that's okay. And now we have the boat velocity in the x direction plus mass of the round, which is going to be 20 divided by 32.2. So you can see that these would actually cancel out, but that's okay. And then we know that this is 2,000 and then sine of 30. So we're going to get the velocity of the boat at state 2 in the x direction. Well, it's obviously going to be negative. And so we're going to take our 10,000, subtract out 20, not a big deal there. And then we're going to divide by 20 and 2,000. Nope, sorry, I messed up. Let me do this again. Let me take these values and then divide by that. So 20 times 2,000 times the 30, the sine of that, and then divide by 10,000 minus 20. And we should get that we're going to negative 2.004 feet per second in the x direction. So the boat's going to go that way because the bullet went that way. It's an equal and opposite thing. And then in the y direction, we're going to say, okay, so we have a positive, the boat, the mass of the boat times the velocity of the boat, 1, and that's entirely in that y direction. Plus there's no impulse going on here. And then it's going to equal to the mass of the boat, or I guess the mass total. Yeah, this is supposed to be mass total right here. I guess that's how I was calling it. This is the mass total minus the mass of the round. And then here's the velocity of the boat 2 in the y direction plus the mass of the round times the velocity of the round 2 times the cosine of 30. So we take our, and once again, I think all these 32.2s will cancel out, but we have the 10,000 divided by the 32.2. Velocity of the boat initially is 30 feet per second, right? And then ignore that, and then we're going to take that, once again, 10,000 minus 20 divided by 32.2 times the velocity of the boat in the y direction, which we don't know, but we're trying to find out, 2 in the y direction, plus mass of the round, which is 20 divided by 32.2, and velocity 2,000, and that's going to be times the cosine of 30. And we can see that these 32.2s are going to cancel each other out, but want to really emphasize, though, that we need to turn weight into mass. So what do we got? We got 10,000 times 30, and then we have 10,000 minus 20. I don't need to do that one yet. All right, I'll save that for the end. So now we're going to have 20 times 2,000 times the cosine of 30. Boom. So we're going to subtract that out from over on this side, right? And then we're going to divide by this other piece right here. Boom. And we're going to find the velocity of the boat afterwards in the y direction is going to be 26.59 feet per second. So it slowed it down, which you can kind of like anticipate that it's going to do, right? It's firing off this 20-pound round. That's huge. And they're throwing that thing out there, and the boat's going to, like, it was going fast, but now it's not going to go as fast because it just shot this thing out there, this reaction to it. So now we have the velocity of the boat. We want the magnitude of it, and so we're going to get 2.004 squared plus our 26.59 squared, and it's such a small thing, it's going to come out to nearly 26.6 anyway. But let's do it anyway. I guess it's the right thing to do. And 2.004 squared plus square root, yeah, pretty much 26.66 I actually got. So I might disagree a little bit with the answer, because as you can see, the answer is 26.6. More like 26.7, man. And then the angle that would form in terms of the boat's motion, it depends on what you call rise and run, but this is rise and that's run, right? So 26.59 divided by 2.004, and well, I need to do 26.59. So, ooh, wait, how come I get something different? I don't like that. Why is my angle different? I don't like that. Try it again. 26.59, 2.004 divide inverse tan. I get 85.69 degrees. We got ourselves a disagreement. Let's find out why. Where are the solutions? Practice solutions. What did I do wrong? I don't know. Why won't this open up? There you go. Read quickly. Look at this sloppy work. Look at how sloppy that is. 26.5. Yep, there it is right there. I guess I just wrote it down wrong. Why do I have 94.3 degrees counterclockwise from horizontal, and they got 85.7, which is what I just got? I don't know. It could be wrong. So I think maybe I should just fix this thing. So the answer was unfortunately, I think it's wrong. But I want to double check what that is. I want to double check that later on. Well, that's not the ones I wanted to open. I wanted to open these. Why'd open a practice one? I don't know. All right, so let's take a look at another problem here after I get my head out of the way. Yeah, I'm just opening this up to remind myself that maybe I want to do this. Something I was just looking at before the review session started, and I'm gonna maybe make that red to remind myself after the session. I just want to double check where I got that from and why I would have written it down. I have pretty good faith in, even though he's a very sloppy handwriter, this is the guy's an MIT graduate that wrote this, so, you know. And he's a very handsome man. So that doesn't mean anything, but his name is Nick. I'm trying to remember Nick's last name now. Yeah. Anyway, I wanted to point out to you the thing I was thinking. Oh, let me move this over. Under useful links and resources, I've told you about this before, but not that you would remember. This guy right here. I think this is a good treasure trove of extra problems to look at, right? These old exam problems from Missouri University of Technology or something like that. This person has left up all of these old exams, and I was actually just looking through these. Unfortunately, I don't see as many for our particular topic down in this, so I might come back to the particle work and energy, impulse momentum equation, conservation, impact. Let's see. So, but anyway, these are for rigid bodies. Yeah. So anyway, yeah. So I guess maybe in these sections, well, particles. Yeah, you need equation of motion. This is Newton's second law for particles. So here's like particle F equals ma right there. You don't need rigid bodies. Yeah. So it's only like these right up here. But if you want to get to these and use them, I highly recommend that you copy this link and you go to another browser besides Chrome, because for whatever reason they don't show up in Chrome, like the pictures for this thing. Like I could try to make it. I could demonstrate to you like some of these. Like if I go to this guy right here, I think. No, he actually showed up, so he's making me a liar. Anyway, there were some of them that didn't work. That's all I'm saying, and then they might work better for you in Chrome. I mean, in Edge. That's why I used it Edge over here, and like you can find an entire exam's worth of stuff. Hey, here we go. Here's a particle, Newton's second law type of problem. This one's rigid body though, so you can't use it, and these are rigid body ones, so you can't do those. Just a warning. But it's you want to go to the you want to go to the particle work and energy, particle impulse and momentum stuff. But I wanted to remind you of their existence because I might actually use some of them. I don't know. So we got any questions? Let's ask anybody more questions to pick from the practice or from homework or from any other, or even just a problem type that you would like to work on.
Sir, like for the problems of exam prep, like when are we gonna get the solution? Because I solved some problems. I don't know if I'm correct or not.
I'm going to put them up tomorrow sometime.
Okay.
I
Also,
was thinking
sir,
I might put it around noon tomorrow.
okay, excuse me, sir. Also, can you like check the fourth problem of kinetic in the kinetic and path coordination? It's in the top.
This
Like that
one?
one, I'm not sure if I did it correctly.
Is this the one you mean?
Yes, yes.
Okay, cool. All right, let's see. So we have this merry-go-round thingy. I don't know what you call this at the amusement park. And the students are reserved to have an angle of 25 degrees, right? They're hanging down at 25 degrees. Each chair, including the passenger, has a mass of 80 kilograms. We want to find the speed of this thing. By the way, this is usually that's a pretty short problem. But okay, cool. So the thing we want to do in that problem is recognize what free body diagram should we make? And that's the big question. What free body diagram? I mean, they show this little thing, and I don't want to waste too much time by drawing the thing out. But I want to talk about the clues that are here that kind of would be there to try to tell you what's going on here. Well, you see, like the thing is spinning right in a circle. Maybe I should have made. Oh, there you go. And so they're all kind of coming. Here's the angle. Here's the line that they would have had if they went straight down. Like here, but here is where the little kids are. They're swinging out, right? Because they're going around. So and as a sort of a clue, they tried to give you a hint by drawing these axes right here. Like I don't know why they decided for B, but you could have called this Y if you wanted to. But you can see that the tangential is going tangent to the path that they're traveling, and the normal is going to the inside. So that's sort of like a clue that the problem author tried to give us, that the tangent is that direction, and the normal is in that direction, and then the vertical would be here. And they decided to call it B for some silly reason. I'd call it Y. So looking at that, you could draw a free body diagram. We don't need to draw the kid. And an IBD of this, but draw it in the Y normal direction. So I'm looking at it this way right here. Looking at it from behind at the thing. So we have an angle. We have a tension right here. And here is the angle they were describing that they wanted us to find. Right, so we also have gravity. So we have weight. Here's the weight of the thing, which we know is mg. And then over here, we have an acceleration. Where is it? What is the direction of the acceleration? Anybody want to guess? Left, right, up, or down?
Say right.
So does that mean it's gonna accelerate outwards like that way?
Is it
It's
left?
gonna accelerate to the tangential acceleration. To the inside, I think, also normal acceleration. I couldn't
So
solve it. That's the problem.
No, but I want you to think. I don't want to just tell you the answer. I want you to try to come to the conclusion yourself.
It accelerated the inside because it turned around.
Yeah, so right there, right?
Yeah.
We're looking at it, or this is the direction we're looking at it. It's accelerating towards the center. If you were looking down upon the thing right here, it's accelerating that way.
Yes.
Because at a later time, it's going to be over here, right? Like it's got a velocity coming that way. And then at a later time, it's going to have a velocity coming this way. So it's changed from that direction to that direction. So it's accelerating towards the center, which is going to be appear in this from this direction like this. So that's going to be mass times the normal acceleration there. So one of the first things we could do is figure out what this angle. Oh no, they already told us the angle. Ooh, they told us. Okay, yeah, they told us the angle. Okay, that's fine. That's good. So all we really have to do here. I know. Okay, so we need 2 steps. All right, so you actually just heard me do the thing that is the light bulb. The aha. And so here is what I'll tell you what my aha was going to be, but I'll tell you what my aha was, but let's talk about how I got to it. So I started thinking about, okay, what's going to happen in the normal direction, the ender. Some of the forces in the end direction is going to be mass times acceleration in the end direction, and we're calling that way positive for this. So I'm going to say, oh, I got ft times the cosine of theta, and nothing else in the x direction there, no other forces, is going to be equal to mass times acceleration in the end direction. But I don't know the tension. Well, then, if I don't know the tension, let's try the y direction. If we ever get stuck somewhere and we have one equation and 2 unknowns, tension and acceleration, let me try for the y direction. So I say sum of the forces in the y direction equals mass times acceleration in the y direction. And I ask myself, is it accelerating in the y direction? No. Is it ever going to go up or down anymore? I mean, if it just keeps at the same speed? No, it's going to be the same vertical. So it doesn't accelerate in the y direction. So all we do is come up to here and we say, all right, we have ft times the sine of theta minus mass times gravity, because it's going downwards, equals 0. So we could find ft times the sine of the 25 degrees they told us that was, minus the mass of 80 times 9.81, because we're SI units. Now we can find what the tension in the rope is going to be. So the tension in the rope, so we got 80 times 9.81, and divide by the sine of 25, and we get that we have 185.7 newtons. Now we can go back up to there. So that's the aha moment, right? The aha moment was like, oh, if I find this tension in the y direction, I'm going to be able to find the acceleration in the normal direction. So I take my 185.7, multiply it by the cosine of 25, set it equal to 80 times the normal acceleration, and I find the normal acceleration. So I take times 25, that's cosine 25 times, and divide by 80, and I get an acceleration, a crazy acceleration. Whee, that's a lot. 21.04, and these are going to be meters per second squared. And can I find the velocity from this?
Okay. Yeah.
Because what does this equal?
That's the inside acceleration. That's also
Yeah,
the
so we can go,
system.
so we can go v squared over rho, right?
Yeah.
So all we need is rho. We need to do a little bit of geometry because of this arrangement. You see that there's 4 meters to this, but this is 6 meters long. So we need to find the radius right in there. So there's a little bit of a extra piece of math that we have to do. You know, the thing, it looks like this right here. There's 4 meters, and then this distance is 6 meters, which is pretty long actually. And then this angle is 25 degrees. So this distance right there, that's going to be the rho that we need, which is going to be 4 plus 6 times the cosine of 25. So we get 625 cosine times, doesn't seem right. No, I think so. No, that doesn't seem right to me. Oh, they were showing the angle. I got the angle wrong. I got the angle wrong up here too. I wrote it down wrong. I looked at it too quickly. Yeah. I don't like doing the angles from vertical, so I made a mistake right there. You see that angle is actually in between there from vertical. So I need to change that in my previous, all my numbers are going to be wrong right here. So let me fix it. So, well, what this should be now is this should be the sine, and this should be the cosine, because this is really the angle right there. That's really the angle. So sine, fix that, and so the values are going to be 9.81 times 80. And now we're going to take the sine of 25. Yeah, 25 should have kind of like jumped out of me.
The drawing wasn't that clear, like to show.
Excuse me?
The drawing wasn't that
Yeah,
clear.
yeah. It probably it was. And I just jumped to a conclusion too, so I like read it too quickly, which is an occupational hazard, right? Boom, and then I'm gonna take the. I just said cosine. Why did I do that? I'm losing my mind. Sorry, cosine of 25. There you go, cosine 25. And divide it out, and I get 865.9 newtons. That's a lot. I'm going to double check it because I don't like how I have trust issues. But yeah, I got the right thing. Okay, so here we go, and we know this is going to be the sine, and this is going to be the 865.9, and so I'm going to multiply the 25 sine times that, and then divide it by 80. Boom. This makes a lot more sense because this was like more than twice the acceleration of gravity. That would be 2 G's, and you'd be flinging kids off, and they would get, that's astronaut training. But here we go, half a G. I think the kids could enjoy themselves at half a G. It'd be way too much. So let's see. This one right here. This is where theta is, and so that should be 6 times the sine of 25. Add 4 to it, and we get 6.536. So now we can find, by taking the square root of this 4.575 times 6.3536. And I end up with getting 5.468 meters per second, and that's the answer that we were given. Does that whole thought process make sense?
Yes, sir.
And then the idea is that how we're applying the stuff that we know already to a problem, like to think through, try to identify a free body diagram that's appropriate, and the physical thing that's like taking place. There were clues that they gave that might make this problem actually, I think, a little too easy, because as soon as the clues were a dead giveaway, right? Like, them writing normal and tangential right here made us know that it was a path coordinates problem. I personally think that some of the things that you should be learning in this class is the ability to identify that it needs to be a path coordinates problem, right? So just be aware. That's my take on the educational value of some problems, are that not only should you know how to do the thing, but you should be recognize that this is the kind of problem where you should be that you need to use a particular skill set.
Okay.
But at the same time, if you ask me during an exam, I don't know what kind of problem this is. What I probably usually do is I kind of like nudge you and go, maybe you want to take a look at these equations right here, right? So this is the one that we were using, right, for that problem.
Yes, sir.
But this is an excellent question, by the way. I really like the question because it requires you to do something pretty. It requires you to make like really 2 big understanding things. First off, that like we have to do something in the y direction first so that we could do the thing in the x direction, and that it's normal acceleration, and you find that from the free body diagram. So I think that makes this a good question. And I have asked a question like this before on an exam. Like there was one with the tetherball problem. I like that tetherball problem. In my book, I took the tetherball problem, but I made it look like Napoleon Dynamite. If you're familiar with the movie Napoleon Dynamite, he plays tetherball in the movie. So.
Okay.
Other types of questions?
For me, I need to solve more. Like now, I solved like 6 of them. I didn't finish all of them, so I'm still.
That's great. That's great. I like to hear that.
in the
How about
process.
Myrna and James? You guys got any like requests?
Can we do S14?
Yeah, okay. Not. I don't know the numbers of them. So I
Um,
like
go down,
down. Yeah, you're redirecting me like
this
that.
one with the circle.
Gotcha. This guy? No. This one.
Yeah.
Yeah.
So I'm gonna
So
let you go. Take care.
okay, take care. This is a curling problem. So this is an impulse and momentum problem. Good. All right. So at the Winter Olympics, curling team decides to try to hit their stone and get both stones into the circle. Just before impact, the magnitude and direction of the stone velocity is as shown. Right. So 4 feet per second. The coefficient of restitution between the curling stones is 0.6, and each stone weighs 40 pounds. It's going to turn out that it doesn't matter that they're 40 pounds, but that's okay. What is the velocity of stone A after the collision? What is the velocity of stone B after the collision? Will both stones move towards the center? All right, so that's a little bit of, I guess, it's a question. Trying to see how you would know that. This last one right here kind of bothers me. I don't like that, but that's all right. We'll do the problem anyway. All right. So here's our stones, and we see their line of action was already given to us right here. The line of action is like, they show this 30 degrees. I get that right? Yeah, I gotta be careful when I get these things right. So this is VA is equal to 4 feet per second. And the coefficient of restitution is 0.6. And each of these things, this is A and this is B. A equals B equals 40 pounds. And choo. Okay. So the first thing to do is to do an impulse and momentum diagram. Initial impulse and then final. Okay, so this one, we already know with many of these problems, they're going to be equal and opposite, so we're totally good with this. Here we're going to have a momentum. I should actually draw it so they're not quite touching, I think, personally. But we'll have mass of A times the velocity of A1. And here, and what we should really do, let's see. Maybe would be a good idea to go this way. Sorry. Gotta get my lead into my pencil. Come on, there you go. We have that and that going on right there. All right, so this would be I should define the coordinate system, right? I should draw that in here. All right, so here is the normal right here, and here's the tangential. So I'm going to decide that this is the tangential and this is the normal direction. That's supposed to be an N. So the one I'm drawing here is the tangential, and then it's going to be massive A times the velocity of A1 normal right here. And then coming out to this way, I'm going to assume that it's going to keep on going MA VA2 in the normal direction. I already know that this MA VA2 tangential direction is actually going to be the same as this, right? Nothing changes in the tangential direction. And then, but now this one is going to have mass of B times the velocity of B2 in the normal direction. And because it didn't have any velocity in the tangential direction to start with, it's not going to have any to end with. So the only velocity it's going to have is in the normal direction. And by making this diagram really is the key to like keeping these things straight. If you ignore this diagram and think, I don't need to do this diagram, you're just not able to organize your thoughts and to see what's physically taking place. So if you skip it, it's your own fault. But we write down the equation we use. One reason why I write down the equation we use is because students are always saying, I didn't know what equation to use. Well, right here, this diagram kind of told you which equation to use. This is the equation out of the equation sheet. The only thing that was available on the equation sheet to tell you what to do. I think actually there is actually something on there. Never mind. So anyway, we're going to go in the n direction. That's the only one that matters anyway to us. And we say that we have MA and I should write somewhere up above to get the numbers of this that the velocity of A in the let's see, this is 30 degrees right here. So velocity of A1 in the normal direction is going to be 4 times the cosine of 30 degrees. So that should be 4.619. And what are these? Feet per second? Sure. And VA1T is going to be 4 times the sine of 30 degrees, which should be just 2, right? And sine of 30 degrees is 0.5, sure. It's 2 feet per second. So something maybe I would have done earlier on. So I go VA. Oh, and by the way, I should make it negative because for some reason I decided normal was that direction. I don't know. I just happened to decide it, so that's we should stick with it. VA1N plus the 0, they cancel each other out in the normal direction, is equal to, and then I decided everybody was negative here. So my choice of being that is positive was a little, but that's okay. Minus MA VA2 and plus, well, nope, I'll make it minus because I'm showing it in the minus direction. MB VB2 in the normal. One thing I could do is I could actually let me go ahead and just make everybody positive. And I could put in the 40 divided by 32.2. We're going to cancel it out here in a second. But here is the value was 4.619. And it's going to be equal to this MA, which is 40 divided by 32.2. This guy, we don't know, VA2, normal direction, plus he's the same mass, right? So he's the same weight, so he's the same mass. So we can get rid of all of them. Yay. So here's equation 1. 4.619 is VA2N plus VB2N. Now we need to use the coefficient of restitution. And from the equation sheet, let's see, we'll go back up to the equation sheet. I'd rather just memorize it personally. But if we need it, there it is down here at the bottom. So they write VB, they're doing the prime, which means the same thing as 2. I might check to see if I've fixed that on the equation sheet, because I really don't like the prime thing. A lot of books use it. I don't like it. So I write down the equation VA1 n minus VB1 n. All right. So VB2, we don't know this, VB2 n. We don't know this. We do know this, 0.6, and we do know this right here. We have to be a little careful with our conventions. I think we're going to be fine. I think we're fine. Yeah, because I already said that I should have made the thing reverse the thing, so I don't think it's going to matter. So we'll put in our 4.619, and then this one is 0. So that just comes out with VB2n minus VA2n equals 0.6 times that 0.4619. So 0.6 times that, we get 2.771, and that's going to be our equation 2 here. Now, we have 2 equations and 2 unknowns. I think I'm going to rearrange this one to say VB2n is equal to VA2n plus 2.771 and stick it back up into this guy right here. So I say we got 4.619 is going to be equal to VA2n plus VA2n plus 2.771. And I'm able to find VA2n is equal to, we're just going to subtract it out, 4.619, the other one subtracted from, and then divide by 2, because there's 2 of those, and we get 0.938 0.923 9239, and these should be feet per second. So I got a positive value, so it does keep moving, but it has slowed down considerably. It was going 4.619 in the normal direction. Now it's just 0.9239. And we're able from this and this equation right here to get the VB2n is going to be 2.771 plus that. So we get it's 3.695 feet per second. And then that's actually the VB2, 3.695 feet per second. And it should be traveling right there at that 30 degrees. But now we need to continue, we need to combine to get the direction of A, right? We need to get, or the magnitude of A, 2, is going to be the initial velocity in the x direction, or I should say the tangential direction, this 2 feet per second right here. If it was traveling, if this is 2 feet per second in the beginning in this direction right here, traveling, we should say downwards at a at this kind of angle. Here, I'm trying to think of what angle it's going to be. I guess it would say that it was 60 degrees from right here is the angle this is moving right here. This is also going to equal to VA2t. So we're going to take that 2 squared plus our 0.9239 squared. 9239 squared plus 4 square root. It's got 2.203 is its final. But here's a little bit of a kind of a thing we have to be careful with. We're going to find, right? So we have to almost make a little sketch. I find is the easiest thing to do. We're going to have we have this in that direction, right? So we want to find the angle between these two, but we have to recognize that that when we get done with that, we have to either add or subtract that 30 degrees from there. So that always kind of messes me up. So that's where I typically would do a coordinate transformation, but I think probably nobody did in the example solution that you'll see later on. So I would stick to that here in a second. But another way that you could do it is to find, let's just call it this right here is going to be this theta, we'll call it A2, theta A2, just to give it a different name than the other theta. And so we're going to have our 0.92, that's the, well, no, that's the normal. Yeah, that should be fine, right? Because we're doing the rise over run here. So this is the normal direction. 0.9239 divided by 2, and you're going to get an angle of 0.9239 and take the inverse tangent, and you get like 24.7, well, no, 24.80 degrees. But that's from this direction right here. We could kind of see that this right here is 30 degrees. So we'd add those two together, and that would be from, so the 30 degrees. But that's going to be from vertical. So we should actually subtract 90. And so what we're going to find for VA2 is it's going to be going 2.203 feet per second, and the angle this forms right here is 35.21 degrees. So no, it is not moving towards the center of the thing. And let's see how we did in terms of our answers. Might have made a mistake along the way. It happens. So I got, yeah, 2 point, okay, I'm off by a little bit. Got to figure out why. Yeah, I don't know why. I must have made a math error somewhere along the way. So, but let me take a look at the solution here. I should rewrite out all these into a nicer, the way I prefer to do things. And so, some of these were, I'm trying to remember his name, Nick Parker. Nick Parker. Really smart guy. I don't see the solution. Where's the solution? Oh, there it is. So, okay, now this is Alicia. Here, make the normal direction. She didn't do the 3 diagrams like I say to do. She has 4 times the cosine right there. Oh, she's always doing that weird thing. Yeah, I really need to rewrite out all these problems. But that 40 went away. And so she's saying, I don't see, I don't see where the differences are, but I'll I'll figure it out. Maybe I'll update all these solutions, but that would take a really long time to do. But I'll do it. I don't mind. All right, so I will maybe I'll post what the difference was in that problem later on.
Okay. That was the only problem that I got stuck on. I still haven't done like most of them.
No, I understand. Yeah, it's still the beginning of the weekend, right?
Yeah. I need to work on all of them still.
Yeah, I hear you. But the process of working through them will pay off.
Yeah.
And I don't know what my math error was. I'm sure Dr. Garcia is correct, and I'm wrong somehow. But I will figure it out. I just don't know. She was always doing that square root of three kind of thing and I don't. Always loses me. Think it might end up being a sign convention thing that I did. I might have been lazy with my sign conventions. I hope not. So what is 1.2 times the square root of 3? 1.2 times 3 square root of 3. 1.721. Yeah, so I got a different number there. When it comes to here. She had 2 times the square root of 3. Huh. I don't know. She had 0.6 times 4 times the cosine of 30. So why wouldn't I get that? I would get the same thing. 4. Oh, you know what? Right from the very beginning is where I made a mistake. From the very, very beginning, it's just sometimes you just want to like cry. Like it was right here. And that should have been obvious to me that 4 times the cosine of 30 is not 4.619. How did that happen? I don't know. But boom, that should be 3.464. So that's wrong. 3.464. That's wrong. 3.464. When we come down to here, where'd you go? Where'd you go? Where did I use you? Right there. 3.464. So times 0.6 should be 2.079. 2.079. 2.079, which you will now subtract from 4. This is also wrong. This was the 3.464. All right, so we had 3.464 and subtract out that, and then we divide by 2. So this became, boom, that doesn't seem right. Now I got a problem, right? So yeah, I got to try to figure it out later. I'm sorry. No, we're good, right? Okay, no, that's gonna be fine. No, this is what that turns into. This becomes 0.6928, and then that we combine with which equation? This equation right here. We add these two together, so that's gonna be 2.079, and add them together, and you get 2.772. So this should be 2.772, and this should be 0.6928. So that should be 0.6928 squared. So we get 2.117. And this angle right here should be 0.6928. Divide by 2, take the inverse tan, and we end up with 19.11 degrees. And we're going to add that to 30, but then subtract out from 90. And we should end up with, I think, 40.9. Let's see, did I get it right this time? I bet there's still something wrong with it. 40.9. Yes, so I got it right. Yay for figuring it out eventually. Sorry about that. How about another problem? It's just you and me, right? Isn't it, Myrna? James lost connection there.
Hold on. Can we do S15? Oh, you don't know. No, it's not this one. It's that one right there. No, go down, go down. It's a work energy problem. Is
this one?
Yep, this one.
Okay, so we got a steel ingot, which is a funny name. So this is the S15 work energy. I don't know how many hours it would take me to rewrite all of these. Which really should do it. It looks like it's going in a horizontal direction, but it gave me like it almost gives me like a feeling like it's another angle. So this is a weird one because of the diagram, and you have to kind of picture what this is actually taking place. This is a spring inside a spring. That's weird, but it gets done. All right, so there are two springs. One of them is longer than the other, and they have different spring constants. And we want to determine the spring constant in the second spring, which I believe is the inner one. Yes, the inner one is the smaller of the two. So the ingot has a mass of 1,000 kilograms, is traveling on a conveyor. Ooh, and it's got a coefficient of friction. That's not good. At a speed of 1 meter per second for the instant shown. So it's actually 0.5 meters away from spring B, it appears to me. And the ingot collides with the nested spring assembly. That means a spring inside a spring. If the stiffness of the outer spring is 5 kilonewtons per meter, determine the required stiffness of the ingot so that the motion of the ingot is stopped at the moment the front of C is 0.6 meters from the wall. Now, the really hard thing here is to try to keep track of all this information. And diagrams are pretty much the only way that you're going to be able to get this, keep stuff straight. A lot of stuff to look at here. I'm going to draw my spring really poorly, but I just want to make sure that it's clear that there are two springs, right? One of them is 0.5 meters long, whereas the other is 0.45 meters long. And this ingot is on this conveyor and traveling at V of 1 meter per second, and his mass is 1,000 kg, and the coefficient of friction is 0.05, and the Ka, so this is A, and this spring is B, is 5 kilonewtons per meter. And determine the required stiffness. Okay, so it's when we're done with this thing, right? So we might want to try to draw this out right here, right? this spring is going to be 0.3 meters from the wall, right? So the del of A, spring A, when that happens, we call it 2, right? Because it's the, we'll say that this is state 2, this is state 1 right here that has occurred right in there. The del that will have taken place will now be 0.2 meters, right? As he started out at 0.5, now he's going to be crushed down to his 0.3. And then the del B in the second state, it's going to be 0.15 meters, right? And then the distance this has traveled, this right here, is going to be 0.5. So if I was going to say that the delta, let's call it delta x, that this thing has traveled, is going to be the 0.5 plus 0.2, right? Because this was where, when it got to right here, this thing got crushed down, so it's 0.3 now. So it has moved 0.2, so this 0.2, so it has moved 0.7. There's a lot of record keeping here, right? A lot of stuff where you just kind of try to picture what's taken place. So now we say KE1 plus PE1 plus the work that gets done between 1 and 2, and then KE2 plus PE2. Now, as I'm going down one at a time, KE1 is 1/2 mass times velocity 1 squared. So that's going to be 1/2 1000 times 1 squared. So I think I could do that. That's 500, right? Newton meters. PE1 is 0. There's no potential energy at the first state. These springs aren't like preloaded or anything, so we're okay there. And it's not going to change in vertical position, so that doesn't work out. The only thing that's taking place externally is going to be friction. This thing is going to be slowed down. Friction is going to rob energy from this thing. So we're going to say minus the friction force times the amount of distance, total distance it moves. And to get that friction force, we really ought to do an FBD and IBD. But it's really not necessary. But what are you going to do, right? You got a friction force happening here, F. We got a normal force, Fn. We got a weight of the thing. And the only acceleration is a deceleration going that in the x direction. So sum of the forces in the y direction equals mass times acceleration in the y direction, which is 0. We got negative weight of the thing, which is negative mg. Plus Fn equals 0. So Fn is just equal to 1,000 times 9.81 for 9,810 newtons. So the friction force right here is going to be the coefficient of friction 0.05 times the 9,810 and times the distance it moves at 0.7. So we're going to get a negative 9.81, not 9.81, 9,810 times 0.7 times 0.05. And we get a negative 343.4 Newton meters, right? And then the potential energy at state, oh, no, I go kinetic energy. I'm going to go kinetic energy, going in order. The kinetic energy at state 2 is 0 because it's when it's going to stop, right? And then the potential energy at state 2 is going to be from both of the springs. So we got K A del A2 squared plus 1/2 K B. That's the thing we're going to try to find. KB2 squared. So you got 1/2. And they gave it to us in kilonewtons per meter. So we really want to use newtons per meter, because we have meters right here, and we got 0.2 squared plus 1/2 KB, thing we want to find, times 0.15 squared. So we can find what those things are. Yeah. 5,000, 0.2 square it times it to divide it, and we get 100 plus 0.15 squared divided by 2, and we're going to get 1.125 E minus 2 KB. So we plug them all back into this original thing, and we say 500. I don't know what I just did right there. 500 plus 0 minus 343.4 equals to 0 plus 100 plus 1.125 E minus 2 KB. KB is equal to, let's see, do that. Do I still have those numbers anywhere in there? No, I don't. That's disappointing. So 500 minus 343.4, and then subtract out 100, and then divide by 1.125 E to make it minus, and I get it's 5,031 newtons per meter. And because they gave us the original one in kilonewtons per meter, it makes sense that we would tell them kilonewtons per meter. And it's slightly off. The answer that I wrote off of what the original solution to the thing, I wrote it down as 5.04 kilonewtons per meter. But like I said, I need to update, I think, this solution so that they look like what I expect students to be doing. So some of the quirkiness of my fellow faculty in writing out their solutions is apparent. Maybe it would make it better if I wrote them all out. Does that make sense, the process?
Yeah, this one is kind of easy, but you just gotta like organize your thoughts.
Exactly. And so much of doing the practicing the problems is trying to organize. Right?
Yeah, but this
so
one
that,
was easy.
Yeah.
But yeah, that's it for me.
Okay. That's cool. I hope this was helpful.
It was.
And I'm available throughout the weekend for individualized questions from people.
All
So
right.
let me know. Hey, have a great weekend.
Thank you too.
Hopefully this recorded.